Hello, my name is Jonathan Conroy, and today I'll be talking about optimal padded decompositions in minor free graphs. This is joint work with Arnold Filtser. So suppose we're given some metric space, which is the shortest path metric over some graph G. We want to partition the vertices of G into clusters, such that every cluster has small diameter, and such that nearby vertices are assigned to the same cluster. Of course, we can't guarantee that every pair of nearby vertices is assigned to the same cluster because then we just end up with one giant cluster. So instead, we ask that our clustering is randomized and that for any pair of nearby vertices, with good probability they're in the same cluster. This is useful for many algorithmic applications, for example, with divide and conquer paradigms. So formally, we say that a graph has a beta delta padded decomposition if there's a stochastic partition of the vertices, such that every cluster in this partition has diameter at most delta, and such that every radius r ball in the graph is cut with probability at most beta times r by delta. And by cut, we mean that it doesn't belong to a single cluster in the graph. Okay, so the parameter to pay attention to here is this beta, which is called the padding parameter. And if a graph admits a beta delta padded decomposition for any choice of the diameter parameter delta, then we say that the graph itself has padding parameter beta. So just to gain some intuition about this object, consider an unweighted path graph. And if we want to chop this into components, into clusters of diameter delta, really the only thing we can do is just chop into intervals of length delta and apply some random offset in the beginning, let's say. So it's easy to see that every edge is cut with probability 1 by delta, and in general, an interval of length r is cut with probability r by delta. So this says that r by delta is the right thing to compare against when we want to chop up more general metric spaces into bounded diameter components. Okay, so the padded decomposition was introduced by Bartal in the 90s, and he showed that every n-vertex graph has padding parameter log n. Moreover, this is tight. For example, for constant degree expanders, we need padding parameter at least log n. So Bartal was motivated by metric embeddings into trees, and some other early work on padded decomposition type things were motivated by float cut caps. But in general, there's just this host of applications. And for many of these applications, the quality of the solution we get is directly governed by the padding parameter beta. It's natural to ask, log n is tight padding parameter for general graphs, but can we do better on restricted graph classes? Because then we get all these improved applications for free. So in particular, in this talk, we'll be talking about KR minor free graphs. So a graph minor of a graph G is some other graph obtained by deleting edges and vertices and contracting edges of G. For example, planar graphs exclude K5 minors, and we'll be looking at the class of graphs obtained by excluding a KR minor for some larger R. So the first padded decomposition for minor free graphs was obtained by Klein, Plotkin, and Rao in 93, even before the padded decomposition was formally defined by Bartal. And they showed that KR minor free graphs have padding parameter at most R cubed. And then an improved analysis of some slight variant of their algorithm was shown to have padding parameter R squared. And then later, through some completely different approach, which will be important for us, Abraham, Gavwal, Gupta, Niemann, and Talwar showed that minor free graphs have padding parameter at most R, and they conjectured that the right answer was log R. Note that there is a trivial log R lower bound that's inherited from general metrics because any n-vertex graph excludes a kn plus 1 minor. So the lower bound for expanders implies a log R lower bound for minor free graphs. So for various special classes of minor free graphs, people were able to show this log padding parameter, in particular for bounded genus graphs, bounded path width graphs, and very recently for bounded tree width graphs. Padding parameter was shown to be log in the parameter of interest. These are all special cases of minor free graphs. And in this work, we show that every KR minor free graph has padding parameter log R. Okay, before I jump into the techniques, I have one more object to introduce, which is sparse cover. So sparse cover is something that's very related to padded decomposition. It's a set of non-disjoint clusters, so it's not a partition anymore, such that one, every cluster has small diameter at most delta. Two, every sufficiently small ball in the graph is contained in some cluster. And the specific meaning of sufficiently small is governed by this parameter rho, which is called the padding parameter. And three, every vertex in the graph is contained in at most tau clusters. Tau is called the sparsity parameter of the sparse cover. Okay, and sparse cover was introduced actually even earlier than padded decomposition, and it has a host of algorithmic applications of its own. So note that if we have padded decomposition, we can construct a sparse cover. So padded decomposition says that any sufficiently small ball is preserved with constant probability. So if we just take log n samples of a padded decomposition, we can guarantee that with high probability, all sufficiently small balls are preserved by some cluster in one of these sampled padded decompositions. So we take our sparse cover to be the union of all clusters from our sampled padded decompositions. So our second main result in this paper is to show something in the opposite direction, that if you're given a sparse cover, you can construct padded decomposition. So in particular, if you're given some sparse cover with, say, constant padding and with sparsity tau, then you can construct an O of log tau padded decomposition. Okay, does this help us get log R padding for minor free graphs? Well, not immediately. So if we plug in the best sparse cover for minor free graphs, this is due to Arnold earlier this year, this sparse cover has constant padding and sparsity 2 to the R. So our reduction just gives another proof of O of R padded decomposition for minor free graphs. So our third main contribution in this paper is to show that minor free graphs have improved sparse cover with constant padding and poly-R sparsity. And now combining this better sparse cover with a reduction, we get log R padded decomposition as claimed. Okay, so for the rest of the talk, I'll try to give you some overview of the techniques that we use. So first, I'll review some existing work on how to get padded decomposition in various graph classes. This is through the bounded threateners program and its specific instantiation in minor free graphs through COP decomposition. And then at the end, I'll tell you about the new techniques that we used to develop our log R padded decomposition. Okay, so let's begin by talking about the log n padding for general graphs due to Bartal. So Bartal used a ball carving argument. So he said we should arbitrarily order the vertices from V1 to Vn. We're going to consider the vertices in order, and for each vertex, we're going to create a new cluster centered on that vertex. So specifically, when we're considering vertex Vi, we sample some radius parameter Ri from some exponential distribution that has mean delta divided by log n. And then we create a new cluster from the ball of radius Ri centered at Vi. And we add to this new cluster all of the currently unclustered vertices in this ball. So maybe this ball contains some vertices that were already clustered, so we don't add those to our new cluster. We just leave them as is. Okay, so we proceed through the graph. We iteratively carve these random balls until we've partitioned the entire metric space. Okay, and so one can show that using the memorylessness property of exponential distribution, that any radius r ball is cut with probability at most r times log n divided by delta. And furthermore, with high probability, all clusters have diameter at most O of delta. And this, with high probability, can be removed and made deterministic by using a, for example, truncated exponential distribution, which is exponential distribution that's conditioned on the fact that we get something between 0 and O of delta. Okay, so it turns out that this ball carving argument is very powerful even for restricted graph classes. So, except for restricted graph classes, we can't just arbitrarily order the vertices. We have to choose to go over the vertices in some particular order, and this is going to lead to improved padding. So the crucial observation is the following. Suppose you have some ball, say with radius r, centered at vertex v, and you want to analyze the event that it's cut. Well, whether it's a cut or not depends only on the sampled radii of centers close to V. It depends only on the sampled radii of centers within distance O of delta from V. The reason is that every cluster has diameter at most delta. So if a center is too far away, the cluster that grows around that center can never intersect our ball centered at V. Okay, so this motivates the following definition, that for any vertex V, we say that the threateners of V are the centers that have non-zero probability to cut balls centered around V. Okay. And one can use the ball carving argument to show uh, that if you have a bound on the number of threateners, then you can get improved padded decomposition. So in particular, there's this rule of thumb that says if every vertex has a bound on the number of threateners, the padded decomposition is going to have uh, parameter roughly log of the number of threateners. And the argument is just this exact same ball carving argument where the radii are sampled from some appropriate truncated exponential distribution. Okay, so this is what Abraham, Gavwal, Gupta, Neiman, and Talwar deemed the bounded threateners program, although the ideas of this were present in some earlier works as well. Okay, so can we use this bounded threateners program in minor free graphs? The first proof of padded decomposition in minor free graphs by Klein, Plotkin, and Rao does something totally different. But Abraham et al. Showed that this bounded threateners program can be executed in minor free graphs, and they used this COP decomposition. Okay, so what is this? COP decomposition is basically some relaxation of tree decomposition, or a variant of tree decomposition, I should say. So minor free graphs have tree width squared n. It means that there's a tree decomposition such that every bag in the tree decomposition has at most squared n vertices. And this is tight. If you consider a squared n by squared n grid, you can't get a tree decomposition with smaller than squared n size bags if you measure by the number of vertices. So what you can do instead is measure the size of the bag by something other than the number of vertices in the bag. So implicit in the work of Andrei for cop robber games is that it's possible to partition the vertices of a minor free graph into paths, and these are almost shortest paths. There's some technical conditions. So it's possible to partition the vertices into these shortest paths such that there's a tree decomposition of the graph where every bag is the union of a small number of these paths. In particular, it's the union of poly R shortest paths if you exclude a KR minor. Okay, and for example, in the grid, you can see this very easily. Every row of the grid is a shortest path, and so it's possible to get this tree decomposition where every bag contains the union of two two rows of the grid, meaning two shortest paths in the graph. Okay. Um, Abraham, Gavwal, Gupta, Niemann, and Talwar gave a modified version of Andrea's argument. And they said that you can partition the vertices of G into supernodes. A supernode consists of a shortest path plus some small neighborhood around the shortest path. They said that the path is the skeleton of the supernode. Okay. Uh, and Abraham et al. Showed that in minor free graphs, you can construct a tree decomposition where every bag is the union of poly-R supernodes. So why did they do this? Um, so they showed that uh, if you grow the neighborhood around the shortest paths randomly, according to some truncated exponential distribution, then you can get some property that the supernodes are all well separated in some sense. Okay, so formally, uh, so the COP decomposition is a rooted tree decomposition, so it induces some partial order on the vertices of the graph. Um, And what Abraham et al. Showed is that if you consider the vertices in this, or if you consider the supernodes in this partial order defined by ancestor-descendant relationships in the tree decomposition, then for any vertex, there's only 2 to the O of R supernodes nearby to V that are above V in the COP decomposition. So in other words, there's 2 to the O of R threatening events if we execute some ball carving algorithm carving top down in this COP decomposition. And so they used this to prove that minor free graphs have O of R padding. Okay, so recently we introduced a variant of the COP decomposition called buffered COP decomposition. Essentially, the buffered COP decomposition gets this well-separated property of supernodes deterministically as opposed to in expectation. And the buffered COP decomposition wasn't introduced for padded decompositions. It was used for some other problems. But earlier this year, Arnold showed that one can view the buffered COP decomposition as providing a deterministic bound on the number of threatening skeletons for any vertex V. Arnold used this to construct better sparse covers for minor free graphs. But this doesn't really help us to try to get log R padding because there's still 2 to the R threateners. Even though we've improved from expectation to deterministic number of threateners is still exponential. And so this only gives us O of R padding. Okay, now let's talk about how to improve to log R. Um, the first natural idea that one might try is, can we improve the buffered COP decomposition so that every vertex has poly-R threatening skeletons as opposed to 2 to the R threatening skeletons? Unfortunately, this seems extremely difficult, and we don't know how to do this. But instead, we design a way to cope with the fact that we have a large number of threatening skeletons in this buffered COP decomposition. And that method is just divide and conquer on the COP decomposition. Okay. So let's sketch this argument. And first, let's aim to get padding parameter log R plus log log n. And we'll use here the simplest version of COP decomposition, just the COP decomposition of Andreae, where we have a tree decomposition, and every bag consists of poly-R shortest paths. So the divide and conquer idea is maybe the natural idea when you're faced with a bounded tree-width graph. First, we're going to pick some centroid bag of this tree decomposition, meaning it's some bag such that after you remove all the vertices in this bag, you split the graph into connected components such that each connected component has at most n by 2 vertices. Okay, so we select the centroid bag, and we consider all of the shortest paths in this bag. And what we're going to do is do the ball carving argument on these shortest paths. So randomly grow balls around all of these paths, or more specifically around a sparse net on these paths. Okay, and these are going to define poly-R many new clusters. And then we're going to remove all the vertices that we clustered and recurse on the remaining parts of the graph. So the depth of this recursion tree is log n, and in each iteration of the recursion, we grow clusters around poly-R many paths. So in total, any vertex sees poly-R times log n threatening events. So this leads to, by a rule of thumb, this should lead to a padded decomposition with parameter log r plus log n. Unfortunately, there's an issue with this idea, which is due to some technical details in the COP decomposition. Roughly speaking, in the COP decomposition, we're only allowed to grow balls downward in the tree. The reason is that if you have a bag of your COP decomposition, the paths in this bag aren't actually shortest paths with respect to the entire graph. They're only shortest paths with respect to some downward graph. And so when we do our ball carving argument, it ends up only being safe for us to grow balls in this downward graph. But this is bad because if we grow a ball only downward from the centroid cluster, this means that we're going to cut vertices, cut edges deterministically between the vertices that are in the centroid bag and vertices that are above the centroid bag. There's no randomness that we can play with here. It's a deterministic cut if we only grow downward. This is bad. So our fix is instead of growing a ball around the centroid bag, we grow some ring in the downward graph. So in other words, our cluster is defined by taking some large random ball and then removing some smaller random ball. And in this way, we get some randomness along the entire boundary of our cluster. Okay. And with this fix, we can execute the divide and conquer algorithm that was described earlier, and we end up with log r plus log n padding. And so I think that this is some interesting conceptual message from our paper that even though the COP decomposition seems like it has this very strict top-down ordering, it's still possible to do some sort of divide and conquer on the COP decomposition. Okay. Then to improve, we want to improve the log r padding. We want to remove this log n term. We do some slightly smarter divide and conquer. So the idea is we're going to remove many bags all at once in one round of the recursion as opposed to removing just a single centroid bag. And the bags that we remove or carve rings around are going to be sufficiently far apart that they don't interfere with each other. Maybe some intuition is that any vertex in the original COP decomposition sees 2 to the r threatening skeletons, and in each round of the recursion, we're going to remove bags to have the number of threatening skeletons that a vertex can see. So ultimately, we end up with some recursive algorithm that terminates after O of r rounds of the recursion. And in each round of the recursion, we carve balls around poly-R many paths. So in total, we have every vertex sees poly-R many threatening events, which leads to poly-R sparsity sparse cover and log-R padded decomposition. And I'll note that this part, we need the full power of the buffered COP decomposition in order to select which bags are far apart that we can safely carve around. Okay, so to conclude, we've shown that every KR minor free graph has padding parameter log r. And in fact, we can sample this padded decomposition without any knowledge of R, the size of the excluded minor. So even if one is just interested in general graphs or graphs that exclude some very large excluded minor, you can use our new padded decomposition, and it's going to be no worse than Bartol's log n padded decomposition. So there's one very natural open question, which is that our guarantees so far are for padded decomposition and sparse cover are all for weak diameter. This means that the diameter of every cluster is bounded by delta when we measure distances with respect to the original graph, the underlying graph G. But you can also ask what happens if we measure distances in a cluster C with respect to the subgraph induced by C. Can we get some strong diameter guarantee? And it's open whether we can get this strong diameter guarantee for padded decomposition or sparse cover with the optimal parameters. Okay, thank you for listening.